So we talk about hash function, right? So we finish the universal hashing, okay, and also talk about how we can construct such a universal hash, okay, function, okay, hash function. So the only thing left is the perfect hashing. Okay. So before we continue, okay, the first thing to remind you, okay, although we don't have too many students here today, okay, next week is the midterm. Okay, next week is the midterm. So so my plan is obviously today I'm going to finish this hashing, okay, as well as like I'm going to talk about the balanced binary search tree, okay. So there will be the what will be covered in your midterm exam, and I also uploaded the sample midterm to the E-class a while ago, right? So although the problems will be different, but the format will be similar. Okay, so I hope like you guys have, will not be surprised like when you come to take the midterm. Okay, so yeah, and I think the TA is going to arrange the seats accordingly. Okay, yeah, I mean, something like that. So we probably need to borrow another classroom for that. Okay, yeah, although we don't have too many students today. I suppose we have more students than we could accommodate in this room anyway. Okay? Okay. So back to the perfect hashing. So what is perfect hashing? Okay. The idea is like this, okay? You are given a set of n keys. Okay, we would like to construct a static hash table of size n. Okay, and this n is, bounded by n a bit O n, such that the search, okay, always take like the constant time. In the worst case, okay. So this problem actually was, if your search space is large, if your hash table is large, okay, this is relatively easy. Okay, this is relatively easy. Maybe let me jump to this one. Okay. So say like our hash table is of size n. That is like n squared. Okay, it is the size n squared. Okay. Then okay. The universal hashing function. Okay, the big H. Okay, class of universal hash functions. Okay, you just randomly pick an H. Okay, from this big H. Okay, to hash these n keys into the table. Okay, the expected number of collisions. Okay, would be at most 1/2. Okay. So this is very easy to prove. Okay. When the hash table is big, okay, is of size n squared, it's easy to prove. You can easily find such a hash function. So like this, okay, we know like because of universal hash function, like the property, okay, if you randomly pick hash function from this big H, the probability that two given keys collide, okay, under the hash function is 1/n, right? This is like the property of the universal hash function. Okay. So this 1/n is 1/n squared because n is n squared. Okay. And how many pairs of keys are we talking about? We have like n. Okay. Like we just randomly pick two keys from this n. So basically, okay, it's n times n minus 1 divided by 2, right? You have this many keys, key pairs. Okay, this many key pairs. So the number of collisions, okay, will be, this one, this is the number of key pairs times, okay, 1/n squared. This is like a probability, a pair of key will collide, okay, under H. So this multiply them, okay, obviously, okay, this one, the result is going to be lower than, 1/2, right? Okay, n squared, cancel out this one, this n minus 1 is smaller than n, so this one obviously is like smaller than 1/2. So what does that mean? It means that, okay, because the expected number of collisions is at most 1/2, right? So you randomly pick one hash function from these universal hash functions. Okay, if there is a collision, okay, then you just just throw away that function, pick another one. Okay, the chance for you to find, number of times, for you to find like a hash function that will result in no collision at all is 2. OK， 因为你每拿一次 hash function， 你的那个就是你的 collision 的那个就是期望值是1/2嘛，对不对 ？OK，if your expected number of collision is 1/2， 那你如果拿一个来，它有一个 collision， 那你拿另外一个，它一定就是平均嘛，另外一个就完全没有 collision， 对不对？ So this is the idea. So because of this, so if your hash table is n squared, is of size n squared, okay, it's relatively easy to find what we call perfect hash where there's no collision at all. Okay? Just 2 tries at most from the universal hash function. Okay? But how about if the table size is bounded by big O(n)? Can we also create something that is like a perfect hashing? This is relatively much more difficult than the previous one. Okay? It took like a while, okay, until somebody like came up with this solution. Okay? So here's the idea. Okay. So it is called two-level scheme. Okay. So it is two-level scheme. Okay. First, like your n keys. Okay, you have like a universal hash function to map to this hash table of size n. Okay. If there's no collision at all, wonderful. We have the perfect hash, right? But most likely, you don't. Most likely, it's going to have, you are going to have some collisions. Okay? So, for those keys that are mapped to the same location, okay, we call them like this is S1, S2, with some SIs that indicate there are collisions. Okay, these are, these keys collide to each other. So then we have we have to resolve. We have another. You need to use a second level hash function. Okay, for each SI. And for each SI, basically we still use like one hash function from the universal hash function. But this time, this SI, okay, say here, these two keys are colliding, right? So we make sure that the size of the table is n squared, because we have two keys that collide, right? So the size of the second level is this table is 2 to the power 2, so it's 4. Okay, similarly, okay, here, okay, if you have three keys that are collided, then the size of this second level table is of size 3 to the power of 2. Okay, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Because this second level is n squared, right? Is n squared. So the chance for the universal hash function to have a perfect hashing, okay, in the second level is easy, as we have discussed previously, right? Okay. So this is how this two-level perfect hashing works. Like first level, this is size n. Okay, this table is size n. Second level, if there are some collisions, the second level, okay, depending on how many collisions we have, which is, we make each SI, if this SI has a size S, then we just make the second level table S squared in size. And then again use the universal hash function to make sure there's no collision. But the issue is, okay, how much space are we talking about here? Right? Because eventually we need to make sure the total number of space, total amount of space is bounded by big O n, right? That's the issue. This one, as I just mentioned, this is size n, so it's not an issue. The issue is small second level tables. The total amount of this second level table, how big are they? How big is the sum of this second level table? Okay. So no collision at level 2. I think I already explained. Okay, but the issues is okay for the second level. Okay, if each SI is of size Ni, okay, then as I mentioned, like we will use like Ni squared as the size of the table for the second level, right? So the total number of Ni squared is represented by this. And we need to show that the expected size of this thing is bounded by N, right? It's bounded by theta N. That is like what we need to prove. Okay, if we have that, then yeah, then we have the perfect action, like with size, big O N, and like each, search take constant time. Yeah. So here, okay, we say that this is like it's similar to like expected running time, Bucky sort. But unfortunately, like Bucky sort is the only non-comparison based sorting algorithm that we didn't talk about. Actually, there are two additional non-comparison based sorting algorithms out there. They are famous. One is Bucky sort. Another one is called shear sort. Okay. Yeah, probably next time I should include this sorting algorithm in the class. Okay. Either like discuss them in the class, or maybe like I'll assign them as like homework or like part of the labs for you guys to practice. Okay. By the way, okay. I think that it's probably not a good idea. I hand wave this part. Okay. So I create a few more slides. By the way, like I also updated the slides in the class to include these few slides. Okay. First, like this is what we want to show. Okay, the expected sum of this Ni squared. Okay, we want to show this is more than 2N. This is what we want to show. Okay, if we are able to show that, then we are able to claim the probability that this the sum of this Ni squared, okay, greater than 4 times N. Okay, this N is basically number of keys, by the way. Okay, it's lower than 1/2. Because you guys probably don't know what Markov inequality is, so I try to give you an intuition. Okay, first you need to understand this Ni squared, they must be positive, right? Ni squared are positive. Any question with that? 这些都是平方嘛，平方一定是正，对不对？应该是它们一定是大于等于零，对不对？ They must be greater or equal to 0. Any question with that? 可以了解。Okay. So let me ask you this: if there was have 0.5 chance that this argument is opposite. We want to prove A implies B, right? We want to prove A implies B. So this the following argument is not B imply not A, okay? Not B imply not A. Okay? So think about this. So if the probability that this sum of this ni squared greater than 4n is greater than half, greater than 0.5, if there was even no 0.5 chance that the sum, okay, could be larger than 4n, then the fact by itself would imply the expectation, this one, must be larger than 2n. Okay? Because if half of that is greater than 4, and the other half, even when they are 0, the other half, even when they are, the other half, I mean, because we know like the expectation is like, the probability times the value, right? The sum of probability times value, right? Okay, so if this probability, the sum of this ni squared greater than 4 and is greater or equal to 1 over half, okay, then, okay, the other half, okay, so when it's greater than 4 and is like a probability is greater than 0.5, then you just multiply this value by 0.5. It's already 2n, right? It's already 2n. The other chance, okay, no matter how small it is, it must be positive, right? It must be positive. As I said, this is n squared. We were talking about n squared, the sum of some n squared values. It must be positive. So the positive value times another small fraction. Okay, it's still positive, right? So it's impossible for this expectation value to be smaller than 2n, right? 你了解我的意思吗？你想想看这个 ，think about this. This is like a not B imply not A. Okay, and why this is the case? You try to think about what is the definition of expected value. With the fact that this value, the value we are talking about is this one. The sum of ni squared. Okay? The sum of ni squared. This value must be positive. It's impossible to be negative. Okay? And if you have like a more than half possibility, this value is greater than 4. Okay? Then its expected value must be greater than 2, right? This is obvious. So if you have not the B imply not A, I mean, if your discrete math, 你的那个离散数学如果有学过 ，not B imply not A 如果是成立的话 ，if this is the case, then we have A imply B, right? So that's so we have this. I mean, like even if you do not know Markov inequality from the intuition, from the discussion, I hope you can understand what we are talking about here. Of course, we haven't proved this part yet. Okay, so then now the idea is we need to prove the expected implication of like ni squared, the sum of ni squared is smaller than 2. We need to bound this expectation. How do we do that? Okay, first, if a bucket has like a if we have like a three element. Okay, for example, DEF. Okay, or that's the bucket. I mean, let's consider the bucket as like the keys that collide. Okay, we put them in the same second level hash table. Okay, so this bucket, or put it another way, the second level hash table. Okay, it has like 3 elements. Okay, we consider this collision to be D collide with DEF, and E collide with DEF, and F collide with DEF. So totally we count it as 9 collisions. Okay, here first the order, the collision of, for example, E and E, and the collision of E and D, we count it twice, right? Okay, even though they are pairs, but we consider the order, right? Okay, this is how we calculate. Second, we consider the element will collide with itself, right? Okay, so now, let's consider, because if you consider this, the size of this table is exactly n squared, right? Is exactly n squared. The reason we want to do this is to make sure the size of the table to be n squared. Think about this. If you have 2 elements, for example, A, B, then we count it A colliding with A and B, B colliding with A and B, so 4, right? Again, it's 2 to the power 2, right? Okay, so this is like how we result in n squared. Okay, so now, if we consider like that, so the expected number of expected of the imputation of n squared, ni squared, sum of ni squared is going to be the same as expected, the sum of x, sum of y, and cxy, where cxy is like indicate equal to 1 if x and y collide. Else cxy is 0. So cxy is like just like it's defined like that. And remember the property I just mentioned. The order matters. Okay, the order matters, and also the element can collide with itself. Okay, so then this expected value is going to be n plus this one, like summation x summation y not equal to x. Expected cxy. Why we do that? Because we know. Remember, I just told you, we consider x must collide with x, right? The element will collide with itself, right? So if you can for every element that will collide with itself, you get rid of that. Okay, so totally, how many elements that will collide with itself? We have n elements, right? So n plus sum x y naught x e expected dxy. Okay, and then then it's like this is cxy. Here the xy are different elements. So this how many pairs are we talking about? With the idea that order matters. So this is like a permutation, not a combination. Okay, so it's n times n minus 1, right? So totally we have n times n minus 1. How many pairs we have? We have this many pairs. And what is this expected cxy when x and y are different? This is 1 over n, right? Why is it 1 over n? Because We are using universal hash function, right? We are using universal hash function. So according to the property of the universal hash function, the probability for two different keys to collide is 1/n, right? So we have this. And also, this n, according to our argument, we say n is of size n, right? So we can replace n with n. So this one cancels out with n. So it's going to be n plus n minus 1. So it's going to be smaller than 2n, right? So we can prove that the expectation of the sum of ni squared is bounded by 2n. Okay? It's bounded by 2n. So, in other words, okay, we have this. So we can imply the probability of like all this the sum of this ni squared is greater than 4n, the probability is lower than 0.5. In other words, okay, you can just randomly get a hash function h, okay, to make sure that it's like this one satisfied. If not, because like the probability for this one to satisfy is like 0.5, right? So if unfortunately the hash function you randomly pick from the universal hash function does not satisfy this, you just throw it away, pick another one. Okay? Within 2 tries, you must satisfy this one. Okay, you must satisfy this one. So once this one is satisfied, it means this all this sum, the sum of this ni squared is bounded by 4n, right? And this one is n, right? So the total size of your hash function is bounded by 5n, right? And so this 2-level hash function scheme guarantee what we call perfect hashing. Okay, in the worst case, you need to calculate like 2 hash function, but still like the calculation number is bounded by 2. That's it. Okay, so it's a very nice property. It is a very nice property. Okay, so any question with that?不是很确定你的了解。This part is not there in the original slide. Okay, the original slide only gives like from here, here, here. That's it. Okay. Oh, and this one as well. But to make sure that it's easier to understand, I created additional slides here. These 2 additional slides. Okay. Just so when we say like a perfect hashing, it means like the worst case, like search for any key is bounded by constant time. So if the hash table is size is big, this is relatively easy. In particular, we point out like when the size is like a square of the number of keys. this is very easy to obtain. Okay, within two tries of the universal hash function, okay, random pick, we are able to find such a hash function. But if the hash table has to be bounded by, a pick O, and then this problem becomes complicated. Okay, so this two-level hash function, basically, in the first level, we just still use the original, but we may result in some collisions. For those collisions, we have a second level hash table, and this second level hash table, each of these second level hash table, the size is the square of the number of keys that collide here. Okay, and because of our previous discussion, so we know like the second level, it's easy to pick like a hash function that result in no collision. Okay, so with combination of the first level and the second level, we have the first hashing. The only thing we need to show is that the total size is bounded by big O. So the discussion here is to guarantee that the total size is bounded by big O. Okay, so this is like a high level discussion of what we just described. Okay, so 你们了解吗？ I hope you guys understand. Okay. Just want to make sure you guys. I just want to remind you. I also updated the handout for this chapter to include like these few additional slides. Okay, so that if you downloaded the handout previously, please download it again. Okay. Okay. So that's it for the hash. Okay, hashing. So in the data structure, I think like probably they don't. Your data structure professor probably do not talk about hashing. Okay, so that's why I try to cover hashing here in the LB class. Okay, and then it's the balanced search tree. The balanced search tree. Okay. So so you guys know binary search tree, right? Binary search tree. I mean, you guys must have learned balanced binary search tree from data structure, right? Okay. How about AVL tree? Yes, right? 你们资料结构有教过那个二元搜寻术，对不对 ？AVL tree， how about AVL tree？ 没有。2, 3 tree, 2, 3, 4 trees. Well, B tree. Actually, AVL trees and the B trees are, what should I say? Like they are sort of important, especially the B tree. B tree is very important. When you discuss like database, because we use database all the time nowadays, right? So B tree is the technique that is used in the data structure database all the time. Okay, so it is fundamental in the database design schema. But 所以你们都没有教过这些。你们 so how about any balanced binary search tree? Any balanced binary search tree? 你们是这样学谁教的？是张慧老师吗？是，我早天跟张副院长讨论一下。这个应该要教了，这个不教，会有点。Okay, I think that at least the ADL tree should be covered by the data structure class. Okay. Anyway, let's take 10 minutes break. When we come back, we'll talk about